closed string argument. Okay, so briefly let's recall what we discussed in the last class. We first looked at the toroidal amplitudes of the closed string. Okay. And what did we find? We found that the answer was, the torus amplitude was Z d2 tau over tau. Then 1 by right, so tau squared, tau to the power 12. Yes, 4 pi squared, I squared alpha prime to the power 12. And 1 over eta of tau squared to the power 12, to the power 24. So and you remember that we said that we were going to integrate our torus over this fundamental domain for tau. There was only one place, one potential location of divergence, and that was in the limit of extremely large tau. Okay. In that limit, we looked at tau being basically pure imaginary, because it almost is. So large and imaginary tau. And in that limit, we found that the zeta was very easy to expand, because eta was 1 plus q, 1 plus q squared. Sorry, so yeah, 3 o'clock, is that okay if you, sorry, 3:15 or so? Yeah. What? 1. Q, 1 minus q squared and so on. And this q was e to the power 2 pi I tau. If tau is large and imaginary, q is very small. So you can take this whole thing and Taylor expand it. The leading terms give you the leading contributions. So the first term came from just keeping the 1 in it. Okay? Now, it was this times q to the power 1 by 24. Okay? And this times q to the 1 by 24, q to the 1 minus 1. Minus. Let me remember that. No, eta is q to the 1 by 2. Our partition function, because it comes like eta. Yeah. The partition function had a minus. Okay? So keeping track of that carefully, the q to the 1 by 24 and to 48 gave us an e to the power 4 pi tau. That's the first. Then plus we got 24 squared times 1. Okay, plus dot. And we had d2 tau by 4 tau squared by 1 by tau to the 2. This was a problem, it was a divergence, but we understood the interpretation of the divergence. It was simply a consequence of the fact that we were expanding around an unstable vacuum. Clearly, this divergence is associated with the vacuum. The zeta function, each state in the Taylor series expansion of the zeta function is one of the states of closed string theory. The state that was given the problem was the tachyon, and it should have given us a problem for reasons we discussed. You're trying to do quantum mechanics about the instability which operates in divergences.
Why don't we change the scattering amplitude?
Well, you would see the scattering amplitude if you did have one. Oh. You see, classical physics about an instability is fine. You know, classically, you can position yourself here, and you're okay. I mean, of course, you see that there is an instability in the spectrum around. You see that? Exactly. But once you start doing quantum mechanics, we had a little discussion on this last time. Just in the harmonic oscillator, an inverted harmonic oscillator, you can estimate the longest time a quantum particle can spend. It's not very long. It's getting like log h bar. You can try to do that estimate. Okay. Yeah. So this is what we're seeing in quantum techniques. We're just trying to do a Gaussian integral, which is not, which goes the wrong way. Okay, so that's the interpretation of this divergence. Every other term was finite. including this potentially worrisome 24 piece. This was not exponential. Everything else was exponentially suppressed. This was not exponentially suppressed, but had enough power or suppression, okay, to be violated. So, one loop partition function, the only troublesome term was this guy, and this troublesome term has a clear physical origin and will not be there when we look at the superstring. As Ronak said, now actually Ronak's comment is a good one, because it will turn out that when we look at the superstring, not only will there be no divergence, but we will get zero for this observable, simply because the string is space-time supersymmetric, and partition functions in a space-time supersymmetric theory are always zero. Vacuum energy is forced to be zero by supersymmetry, right? Because the supersymmetry algebra tells you Q alpha before x, beta dot. So if you have a vacuum, it's annihilated by Q and Q bar, must be annihilated by P, being particular by energy. Okay, so the partition function we're computing would not be divergent, but would in fact be zero, and that's not very satisfying. Things that are zero somehow don't feel very satisfying. However, there are two things. The mechanism we're discussing goes over also to scattering computers. Okay, and goes over also to finite temperature partition functions, which will be non-zero even in the superstring. But just because there was no tachyon, this term will be just entirely absent in the study of the superstring. So all these closed string one-loop amplitudes, which suffered from divergences in the bosonic string, will not suffer from any divergences in the superstring, just because of the absence of the tachyon. So the only divergence in the bosonic string is there. So divergence in IR divergence, whose explanation we understand it exists because there existed a tachyonic state. Only divergence, and if you tweak string theory somehow to get rid of the tachyonic state, you remove all divergences at one loop and in fact at one loops. Wrap it up. In the closed string. Yeah, please.
Last time you said that open string is on another divergence.
Closed string, we don't do the closed string. Yeah. Okay, so this was our analysis for the closed string. Any questions about that? Okay. Then at the end of the last class, we also went through the same analysis for the open string. Okay? The analysis of the open string is very similar. We had integral dt by 2t as the measure. We had 1 by t to the power 1 by t to the power 13 times now 8 pi square alpha prime. The extra 2 being because the extra 2 is the 0 1 sector. And then we had just an eta of it to the power 20. Okay? Why did we have 24 rather than 48? Because it's effectively just the whole of it. Okay? You remember the boundary conditions of the open string forced us not to have these rectangular, these parallelogram type tori. It's just strips. And therefore, the three-dimensional moduli integral will go over to one-dimensional moduli. Okay? And, great. Now, once again, there are two kinds of divergences. Okay. Now, in this case, there are two kinds of divergences. The first divergence was at t goes to infinity. Okay? A very similar analysis applied to that divergence. Okay? We had a very similar analysis of that divergence. T goes to infinity. We expand the eta function. There's one term which is the tachyon, which is exponentially divergent. There's a next term which corresponds to the gauge bosons, which is exponentially neutral, neither divergent or convergent, but is power over convergent. And then there were subsequent terms which were exponentially convergent. Okay? So once again the IR end of the open string, namely t goes to infinity. Okay? This is each open string mode going over a very large circle. Okay, so the IR end of the open string was completely valued. Apart from a divergence associated with the open string theory. Once again, in the superstring theory, if you have no open string tachyon, as we will not have when we do this, we will not have any problems. However, with the open string, unlike with the closed string, our integration domain was p is equal to 0 to infinity. So now there were two boundaries of this modularization. T equals infinity, which we just talked about, but there was also t equals 0. And the next question is what happens at t equals 0? So you remember how we analyze this. We analyze this by modular transform. Okay? We analyze this by modular transform. Okay? We said that, well, we know that eta is a function which has nice modular properties. How? Yeah. So eta to the 4 times p was modular indirect. How did we know that? We knew that because eta squared times square root t, 1 over eta squared times square root t was the partition function of the free boson. The free boson was obviously modular. Okay? So we use that to re-expand, to rewrite this expression in terms of an eta of 1 by t. Okay? And when we did that, we found that the modular transformation ate up all the powers, 12 powers of these t. dt remained by dt by t squared, which was just d of 1 by t. So when we define the new variable t prime, we simply got dt prime, then some numbers we care about. That's 1 over eta of t prime, I t prime, to the 12. Okay? And then we looked at this expansion. We looked at this expansion at t prime, now very large. T was very small. So it looks very similar to what we had here with one difference. The difference is that the powers are gone. Now because the powers are gone, the first term gave you a divergence. Very much like what you had above. So we got an e to the power 2 pi t divergence. So we have dt, and we're looking at dt prime, we're looking at large t prime. First term was e to the power pi t prime. The next term was 24. And then you had things suppressed plus some number that is minus 2 pi. This clear? This gives you a divergence. But you remember, we reinterpreted this diagram. You see, we have the cylinder. We have a cylinder with boundaries. The first end, which was p goes to infinity, was the end in which the cylinder circle becomes very large compared to the size. That was the IR end as far as open strings. That was IR open string physics. The other is UV open string physics. But we realized we could equally well think of that as a cylinder of fixed size, but propagating over a very long distance, like a normal transform. And therefore this became an IR, this became IR closed string physics. Okay? So it's a general fact that one loop in open string becomes a tree-level propagation problem for closed string. You can see this in your head. A cylinder, if you cut it like this, is an open string going around in a loop. If you cut it like this, it's a closed string. We talked about how this was really the amplitude of propagation between two special states. These states were called boundary states. Okay? So this is an overlap amplitude. Okay? There's an overlap amplitude for a clostering propagation between these two special states. And then we discussed what we expect on general grounds for such an amplitude. So let me first generalize this amplitude. Suppose instead of computing just the partition function, we have computed scattering of open string states. So say that we have some number of insertions here and some number of insertions. Once again you get the same picture, except you would have some number of insertions. Now what would you have? Now you will have the same kind of thing, except that there's some net injection of momentum. Let's say some momentum P in here, and sucking off of that momentum here. Whatever's injected here is eaten up here because of momentum P. Okay? And so what do we expect? Because we're in this limit where we're propagating over very large distances. Well, you expect the first term, the lightest term. You expect some series which is matrix element squared divided by p squared plus n squared for all of the states of the closed string. Okay? Now, doing the integral, let's forget about this guy. Doing the integral for any of these guys, okay, gives us precisely 1 over the coefficient of this t prime, which was this a squared. Were we to have done for the scattering amplitudes, we would have got an extra factor of, for instance here, p prime into minus 2 prime plus p squared, alpha prime p squared. That's how it would have appeared had we put it in the scattering. So we would have this just because it's vertex factors. In fact, it's a nice exercise to see. Okay? And doing the p prime integral would give us each of these poles. 1 over p squared plus n squared. Okay? So you see that what we've seen here is precisely the structure we expect for long distance exchange via closed strings. We get a sum of poles. Okay? Now, let's go back to the partition function. Going back.
What will these insertions correspond to in the open string?
The insertions of, let's say, gauge bosons. Any open string vertex object. It doesn't matter which. Suppose you were interested in computing some scattering process. Let's say you're interested in computing gluon to gluon scattering and one more. Okay? You will have to insert your gluons in all combinations. One way to insert it would be 2 gluons here and 2 gluons there. Such a thing would contribute, for instance, to that process. Okay? So you see that this process with these insertions is very nicely going over from this kind of formula, if you believe that the main effect of putting these p's is just this multiplication. It's very nicely going over precisely the sum over poles with some numbers, exactly as you would have predicted on general terms. In fact, what those numbers are giving you a prediction for the overlap of every propagating state with the state that you start with this boundary state. Because what you do is decompose the boundary state into a sum over closed strings and then each of the closed strings propagates. Is this clear?
24, what is it? P equals 0?
Exactly. Now this 24 was precisely the thing for n squared equals 0. You see? And this dp24 gives you infinity. And that infinity also has an interpretation here. This was just 1 over p squared and m squared equals 0. But also when p squared equals 0. That was an infinity. Okay? The 24 was just because you had 24 polarizations of the graviton. Actually, you have 24 squared, but the boundary state only has overlap with states that are equal on the left and right. So that's the 24. Okay? So we have a second divergence for the open strings. And we also have some sort of interpretation for it from IR physics, but IR physics for the closed strings. So now, great. The reason we have this divergence is that the boundary state, from closed string point of view, has a non-zero overlap with the gravitons. That at zero momentum creates the divergence. And then we had this little toy model of massless physics, in which we understood why that happened. Do you remember? We looked at the model. We understood. So see, suppose you take a massive scale, first a massive scale, and then you add a small term to the Lagrangian, a small source term to the Lagrangian. That doesn't destabilize the thing very much. You just complete the square one, shifts the minimum within that. But if the mass was not there, there's nothing. Yes, it just slopes down. So the only solution for this is phi to rho. So adding a source for a massless field causes an instrument. Removes the vacuum from the field. Adding a small source for a massive field doesn't do any such thing. And adding a small source for a massless field removes the vacuum. And by adding these open strings, apparently what we've done is source the gravitons. Why not? Open strings, like everything else, should carry energy. Okay? So what we've done is somehow, by adding these open strings, given some non-zero source of energy for the closed strings, including the massless closed strings. And that is causing this incident. We see this very clearly in this exchange. Okay? So the naive conclusion would be that closed strings coupled to open strings give you inconsistent physics, so at least are described by a vacuum that we don't yet understand. The vacuum phi equals 0. Problem, it's not a vacuum. It's not close to the right vacuum. Okay? And that's true. If you just take closed strings and open strings and put them together like this, look at a theory where you have both closed strings and open strings and nothing else, this gives you an inconsistent theory, at least in the sense that we talked about. This problem, by the way, again, is 1 by p squared, is called the problem of a Dilettante diaphragm. Equally simple as a graviton diaphragm. It's that you're adding a source in the theory for all of the string fields, but in particular for massless fields. For the massive guys, it doesn't matter. But for the massless guys, it causes a runoff. Okay? So we want a string theory in 26 dimensions or eventually. And this problem, by the way, will continue to the superstring because it has nothing to do with the tachyon. It's entirely about the physics of the massless center. Okay? So if we want to get a consistent theory of open super, closed strings we're fine. Closed strings, no open strings we're fine. Suppose we want to get a consistent theory which has both closed and open strings. Okay? We have to do something else. And the question now is what do we do? Okay? So we have to tweak the physics of the string somehow. And of course people tried various things. And they finally came up with something that worked. I'm now going to tell you that thing. It's called the unoriented string. Okay. So the idea is the following. Let's first look at closed string. So we've got this closed string, and there's this action del x mu. Okay. We have nice mode expansion for the closed string. X mu apart from that is the zero mode. I'm writing non-zero mode parts. With alpha mu by n e to the power I n sigma plus alpha mu tilde by n 1 minus I. Sorry, this is tau plus sigma tau, or maybe this was tau minus sigma, this was tau. Okay, this string lives on a circle of length 2. Okay, now the idea of trying to make the unoriented closed string is to mod out the string world theory by symmetry that it preserves. And the symmetry that you're modding out by is the symmetry of orientation rules, which is you want to identify the configurations x of sigma, I mean, you want an operation, the given x of sigma will take you to x of 2 pi x. Okay? So let me define the operator omega, or the operation, classical operation. This will suit the quantum. Okay, let me just do the quantum. So suppose I have a string, the world, the Schrodinger function of the string, psi sigma. Omega is defined as omega acting on the Schrodinger function of psi sigma is psi of x of 2 pi. Because we want to preserve Lorentz invariance. Okay, so this is just so far an operation. I want to define an operation that acts in a Lorentz invariant manner. So that acts on all x mu's at the same time. Okay. Now, this is clearly a symmetry of the theory. Because if you think about it, all that you're doing is trying to decide whether to view the string this way or that way.
More than that, we are basically folding up the string.
Well, let's look at the string as 0 to 2 pi, where 0 and 2 pi are identical. Okay? Sigma runs like this. So you start from this point and run that. 2 pi minus sigma runs like this. So you start from this point, which is the same point. Oh, not that matters. And run that way. So, the operation, I've not yet defined an identity. The operation is simply changing this way to that way. Okay? If you had a string, look, either you measure sigma as going clockwise or counterclockwise, right? Counterclockwise or counterclockwise. If it's the opposite for you. Okay? Yeah, the fact that it's opposite for you makes it clear that it should be a symmetry. Swear that. Okay, so of course you can check it formally by putting it here, that's clear, right? Because this is del sigma squared, so the two minus signs cancel. So it's a symmetry of the action. Not to be, just some almost trivial thing. Now the non-trivial point is to take this symmetry and make it a gauge invariance. That is to gauge this symmetry of the worldsheet of the string. Okay? Treat as a gauge. Okay, now I'm going to ask what this treating omega as gauge does to the oscillators. And that's easy to answer once you look at this. See, suppose you replace sigma by 2 pi minus sigma. The 2 pi does nothing because it's e to the power I n times 2 pi. Okay, same thing. But the plus and minus do something. They change what you call left movers to what you call right movers. So you see, in its action on oscillators, omega acting on alpha n is alpha tilde. This is clear? Okay. So we understand now how orientation reversal. Okay, this gauge theory acts, the symmetry that we're going to gauge by how it acts on the oscillators of the closed string. It just takes a left mover to the corresponding right mover and vice versa. You see, look at here. What this operation does is just change the sign of sigma, right? It's a 2 pi result. But whatever multiplies tau plus sigma with an n is identified with alpha tilde. And whatever multiplies tau minus sigma is identified. So it just reverses. So it's omega acting on alpha n is alpha tilde and omega acting on alpha tilde is alpha n. Okay. So what we're doing is to gauge the theory by this exchange state. It's clear what we're going to do, right? We're going to end up keeping only those states that are doing the same thing on the left as on the right.
So why do you call it gauging the symmetry?
By gauging, I mean we're going to impose this as a projection on our states. You see, so what's the difference between a symmetry and a gauge symmetry? A symmetry is, a symmetry of the problem that leads to degeneracy. There are physically different states in the theory that have the same properties. A gauge symmetry, on the other hand, is an operation by which you take something that would have been a symmetry and just say all states that are related by this operation are actually identified to be the same state. Okay, that's what I mean by gauging. Okay, so now let's quickly see what impact this gauging will have on our computation of the torus partition function. Okay? This thing does nothing to the zero modes because the zero modes are independent of zero. Okay? So the zero mode sector is unaffected. So now what we're going to try to do is to try to do the computation, the partition function computation at one loop for the unoriented closed loop. Is this clear? Right. So, the way I'm going to do it is this. Because I'm gauging is imposing the projection that only those states with omega equal 1 survive. So that's imposing putting inside the trace of q to the power L0, q bar minus 0 bar. Just adding this projection of the trace of 1 plus omega by 2, where we use the fact that every state has eigenvalue either 1 or minus 1. Omega squared is 1. That's clear, right? Because if you do this twice, you get back to yourself.
Why is it, how is it different from just gauging the range of sigma from 0 to pi?
How is it different?
Well, I mean, basically just taking a string and folding it up.
We're saying that the string viewed this way should look the same as the string viewed that way. I don't see how that's folding it up.
You're saying that x of sigma and I got confused about the same thing. They're different x of sigma.
Yes. Okay. Great. So, in the same formula as before, so we will get d2 tau by 4 tau 2 squared 1 by 4 pi squared tau 2 to the power 12. None of this has changed. Okay? But then, instead, the stuff that gave us the etas, okay, that's different. The stuff that gave us the etas is different. That stuff is to be replaced by trace of 1 plus omega by 2 q to the power 0 q bar to the power 0 bar. Where the trace is only over the oscillators and also includes the zero point energy. Okay, the 0 point energy is unaffected by all of this, it's just standing outside. So we're looking at the oscillator trace and then we'll add the appropriate q to the 1 by whatever, 24. Okay, so we'll have, let's put that. We'll have q to the power 1 by 24, q bar 1 by 24. Both with minuses, 2 to the power 24. Okay, and now we've got this trace which is purely over the oscillator sectors under the convention that the oscillator vacuum has energy C. Okay. Now how do we deal with this? Well, one way of thinking of, there are many ways of doing this, but this is a convenient way. One way of thinking of it is to split this up into two terms. One is just half into whatever. So that's just half of what we have for the closed loop. Okay? So it's just half of 1 by eta tau to the power 48. Okay, so let's not take this. including the 0 volt contribution. 1 by eta tau to the 4.
Where is the
Well, I'm trying to understand what happens to unoriented pure strings. We introduced orientation reversal to see if we can deal with the problem of tadpoles caused by putting open strings. So what we're going to see in the end, just to see where this is going, is that unoriented strings, along with open strings, okay, can make a consistent theory. Okay, but if the strings are unoriented, both the closed string sector as well as the open string sector will have to be unoriented. So I want to redo the calculation of the partition function just for the closed strings, and then we look at it again for the open strings. Okay. Now let's look at this guy, this omega by 2 q to the L0 q to the pi L0. This is the Newton. Okay, so this term is what? It's half. And now how does omega act? You see, omega acts as follows. If you've got, let's say that you've got some number of excitations of the left mover. Let's say you have, let's look at a particular, let's say the nth left and right. Okay, so if you had alpha minus n to the power mn and alpha tilde minus n to the power m tilde acting on the vacuum, what does omega do? It just switches where the tilde is. So this state was labeled as mn and tilde. Okay? If this state was labeled as mn and tilde, it just becomes m tilde mn. Now what have we got? We've got a trace. The trace only takes into account those states in which the left and the right are the same. Okay? So only those states which have equal number of left and right moving oscillations will contribute to this case. Is this clear? Okay? So only those things that will have equal number of left and right moving will contribute to this trace. And therefore, this part of the partition function becomes very similar to an open string partition function. Because this part of the partition function isn't something separately over the spectrum of left movers and right movers. It's something only over the spectrum of left movers. Okay. And so what we're going to get? We're going to get q bar to the power L0. Okay? We're going to get q bar to the power L0. Now, this q bar to the power L0 is what? Where L0 is just the spectrum of either the left movers or the right movers. Okay? Now what is Q? 2 was e to the power 2 pi I tau. Q bar was minus 2 pi I tau bar. That's Q bar. So this is equal to e to the power 4 pi I tau 2. I into I tau. Thank you. Minus 4 pi. Minus 4 pi tau 2. Okay? So now what we get is something extremely similar to what we have in the open strings. Okay? There we had everything dependent just on the speed. Once again we have everything dependent just on tau 2. So one real thing. The only difference is that in the open string we had 2 pi minus 2 pi tau. Okay? Whereas for the closed string, now we have 4 pi tau 2. So this becomes, so this part of the partition function becomes 1 by 2, okay, and 1 by 2 eta of 2I tau 2 to the power, and then this comes to that. Is this clear? Okay. Now we're going to re-expand what happened. Okay. So once again we can look at this thing at large and small tau 2. At large tau 2 we have the same, no problems if there's no tachyon. At small tau 2 we're going to have a very similar issue. A very similar kind of divergence that we had for the open string. Okay, we're going to have a very similar divergence that we have for the open string, except for this divergence now, a very similar divergence, and there may be some halves different and so on, but it's clear that it'll have the same sign.
Can the modulate be evaluated for ordinary difference?
Yes, we did. Okay, now I have to explain. Good, so we did. It becomes the same as moduli space for the open strings. I have to explain this. I have to explain this, and I have to explain this thing geometrically. These are the same things. I should soon give you the floor. Okay, let me just give 5 minutes. Yes, you do. Just take it from me, and I'm explaining it afterwards. Okay, but you see that what you get here. Now, once again, we'll do the same modular transformation. In doing the modular transformation, we'll pick up some factors of 2. Because, you remember the modular transformation was tau 2 times eta to the 4 is modular invariant. Okay? So if we have a 2 tau 2, we will pick up, we'll make it by of eta of 1 over this, so 1 over tau, 2 tau 2. But also in the eta outside, there will be extra factors of 2. Let's do that. Okay, so let me do that. Get the numbers. Okay, firstly there was this overall half that came from the half, and that is going to be in every diagram, so it will not play much of a role. But the important factors of 2 come from the following. We had tau 2 to the power 12. So okay. Actually, we should keep track of all factors.
Yeah, then there is one more over 4 pi square.
One more
Because it was 4 pi square tau 2 raised to 30. So
we should keep track of all factors. You're right. Okay, let's keep track. What's important is the relative factors between what happened with the open string and what's happening here. So let's say the open string has 1 over 8 pi squared to the power 13. Okay. What we have here is half, because of the half into 1 plus omega, times 1 over 4 pi squared to the power 13 into 1 over tau 2 to the power 12 eta of 2I tau 2 to the power 12. Okay. Now, suppose I put a factor of 2 here, and then a 2 to the power 12. Now this will be exactly like the open string, except with an eta with 1 over, with a different effective value of tau. And that will have exactly the same divergence for the closed string sector, the same 24 over here. Because the part that gave the divergence was independent of tau. Okay? So the effective factor that is appearing here, okay, the effective factor that is appearing here is a 2 to the power 12 times 2 to the power 13. Because we should compare with, we should put 8 pi squared to the power 13. And then there's a half here. Sorry?
And one more two for changing the for Jacobian of tau to tau.
Yeah, that's probably right. That's probably right. So, and let's do that. So, we showed that the original thing was good point. So, the original thing was d tau 2 by tau 2 squared. Yeah, it's a question of where that goes. I think we'll get an extra factor. Excellent. So the whole thing is this extra half, which will appear also in the open strings once we make them unoriented, times 2 to the power 20. And it appears with the same sign. Okay, so we had a problem with open strings. We have the same problem with introducing non-orientation into closed strings. In fact, it's a problem that's even worse. This is extra 2 to the power 24. Doesn't look like anything very good is happening. Now, one more thing about the open strings. 5 minutes more. One more thing about the open strings. I had done the thing with Chan pattern factor with no Chan pattern. But had we had the ordinal UN Chan pattern factors, the open strings would have had the same problem with a factor of n squared. So suppose we have the overall problem with the open strings, we get n squared. Closed strings have no Chan pattern factors. So they contribute with a half times 2 to the 24. The half is in the middle. Okay? And the key point is relative side is plus. Nothing scientific. N square can't be made negative, 2 to the power 24 can't be made negative. Looks like we're stuck. Looks like we're stuck, except for the fact that once you introduce non-orientation in the closed string set, you should also introduce non-orientation in the open string set. Okay? Now I'll very quickly tell you how this works. We'll leave the details for next time and then have a how do you make an open string expression from here to here now? So clearly sigma is equal to pi minus sigma. Now let us recall what the states of the open string with our boundary conditions. Okay? So our boundary conditions were that the derivative of the open string vanished here and here. Okay? So how does that work? Suppose we have cos n pi sigma, and at sigma equals 0, the derivative vanishes there. And at sigma equals n sigma. Sigma equals pi, the derivative vanishes at the other end, because it's always cosine of pi times something. Times n, which is always whose derivative always vanishes. Okay, these were the modes. So the nth mode in the open string was multiplied by this factor. Now what happens to this mode if we use sigma goes to pi minus sigma? Okay, so what's cos of pi minus sigma? Minus cos pi. Minus cos sigma. What's cos of 2 pi minus sigma? Sorry, what's cos of 2 into pi minus sigma? It's same as cos of 2 into sigma. The extra factor of basically what this does is take alpha n goes to minus 1 to pi n. Can you fix yourself? This is clear, right? So the action of open strings is more interesting. You see, it could not be interchanging because there was only one state. There was no separate right move and left move. What the interchange of left and right does is give signs to states, minus signs for odd end and plus signs for even. Okay, so far so good without Chan pattern factors. Now if you add in the Chan pattern factors, what do you think that should happen? We've got an index I here and an index j there. The most straightforward thing to do is to say that just gets replaced. So it's I goes to j goes to I. Okay? This is the most straightforward thing. Actually, that's the most sophisticated operation that one can try. Turns out not to be relevant for what we're doing, so I'll discuss it very quickly. But certainly it's intuitive. You just interchange because you're already reverse it. You interchange I and j. That's very nice. That's very nice. Let's take 2 minutes to see. Let's take. Let's take 2 minutes to see what it means that a state is invariant under omega. So how do you make a state? You make a state by acting with a bunch of alphas, and if it has some ij structure. Okay. So now instead of looking at an ij structure as we did before, we can look at this ij structure as a matrix and use some basis for these matrices, these lambda matrices that we did before. Okay. So suppose we got some matrix lambda and some bunch of oscillators acting on the vacuum, acting with omega does what? It takes lambda goes to lambda transpose and it acts with appropriate signs on the oscillators. So if you've got a definite oscillator number, either you get +1 or -1. Okay? So let's see. Let's suppose we're working first with a tachyonic state. So there are no oscillators. Then all that you get is lambda goes to lambda transpose. Okay? If your state has to be invariant under omega, what does that tell you? It tells you that lambda had better be a symmetric matrix. On the other hand, let's look at the gauge boson state. It has one alpha. Alpha goes to if you have it has alpha 1, alpha minus 1. That picks us a minus sign. So if it's going to be symmetric, invariant under omega, the omega operation, the lambda behind it has to be antisymmetric. So this is what it does. Different states, the projection, the requirement that things are invariant under omega tells you that different states in the omega in the open string spectrum either appear with symmetric or antisymmetric Chan pattern indices. Crucially, the gauge bosons appear with antisymmetric Chan pattern indices. What does that tell you? That you remember ordinary gauge bosons had gauge group UN. That's because the Chan pattern indices were just arbitrary n cross n matrices. Now these Chan pattern indices have become antisymmetric. What does it tell you about the gauge group? SOA. Okay? So when you mod out open strings by orientation, by the orientation operation, you will make the gauge bosons SON. Actually, the subtlety I told you about gives you another option. The option is that of SPN. When we need it, we'll come back to that. Okay? Really 2 minutes. Okay. So now what we've got, so this is the structure of unoriented open strings. Now what we want to do is to redo the computation of the partition function of the open strings, allowing them to be unoriented. Once again we use the principle of simply inserting the factor 1 plus omega by 2 inside the trace. Okay, no problem. 1 plus omega by 2 inside our trace. This part contributes just like open string state, but with a factor of half. Good. So that's this extra option. So the full n square. So that's just 1. What about the stuff with the omega? You see, how does omega? First, let's see how it acts on just the Chan pattern indices. Because action of Chan pattern indices is completely. If you need coffee or something, go ahead. It's fine, don't leave. Go ahead.
Oh, maybe I will.
Okay, so the action on the Chapman indices is independent of the action on the oscillators. Chapman indices are reversed, and oscillators become a minus sign. Okay. What about the so when we're doing the trace, we're doing the trace over all n squared copies of Chapman indices. Now we get +1 on symmetric guys and -1 on antisymmetric guys. So what's the net factor you get? In the trace over Chapman. Suppose trace over matrices, all n cross n matrices, counting matrices that are symmetric as +1 and matrices that are antisymmetric as -1. What will you get? N. Because how many symmetric matrices are there? N to n +1 by 2. Each of these gives us a plus. How many antisymmetric matrices? N to n -1 by 2. This minus this is n. Okay. So now we want to see what we're going to get from the other thing. Whatever it is, will come with an. I'll call it n. Whatever it is will come media n. That's just from the template. Okay. And now we have to do the oscillator sum over the test. This was okay. So the 0 point energy doesn't change. What about the oscillator sum? The oscillator sum, well, for each copy of an odd moding oscillator, we pick up an extra factor of -1. Okay? So we will get 1 over 1 plus q over 1 minus q squared. 1 plus q cubed over 1 minus q cubed. That's all. You see this? Okay? So it's exactly the same eta that you would have got for the open strings. Except that in the eta for the open strings, all these are minuses. Is this clear? You see, if you Taylor expand this, it counts the term with 1 minus oscillator with a minus sign, but 2 minus oscillators with a plus sign. Exactly as you would. You should think of this as 1 minus minus and 1 minus minus q. You see, that's exactly the right answer. Okay. Now we'll give the floor to Rona. I'll do the calculation also explain why the modular parameter ran only over the open string thing for the Klein model, oriented closed string diagram that I postponed to later. I'll do that next class. But let me just quickly tell you the answer. We'll justify this. When you do, now what you have to do is compute this object and look at what happens to a testing coefficient. The way you do it is to do a modular transformation. The interesting thing about it is, once again, you get a divergence, but of the opposite side. Okay? And turns out that divergence is minus 2n times 2 to the other. Firstly, I messed up. Where is this? I'm sorry. This 2 when is it? Right came up here. I'm sorry. So this was 2 to the power 13. Sorry, 2 to the 26. Yeah, this was 2 to the 26. I'm sorry. This was 2 to the 26, not 2 to the 24. Sorry about that. And here, this was 2 to the 26. And here, when you do this, you get 2 to the power minus 2n and 2 to the power 2. I'll show you this next class. I'll also we do the two countings carefully. Okay? So that is what? That is half into 2 to the 13 minus n square, which is consistent if n is 2 to the power 13. So, open strings with closed strings give you a consistent tadpole free theory, provided you choose a particular value for the Chan pattern. You look at the SO 2 to the power 13. Now in the superstring, this 13 which is d by 2 just is replaced by 5 because the critical dimension for the superstring is there. So the analogous statement is that you can SO 2 to the power 5. 2 to the power 5 is a more civilized number than 2 to the power 14. So SO we choose it. Okay? And the theory that you get by including orientation, the unoriented string, along with open strings in the superstring has a name, it's called type 1 theory. Okay? So, so the requirement of lack of a tadpole, the existence of a good vacuum, allows you to put open strings into the theory, but only if they're also accompanied by this orientation reversing gauging. Okay? So, an unoriented open string theory coupled to closed strings is, as far as we understand, in the superstring, consistent theory. But only with a particular number of Chan pattern indices, namely 32. Okay? We will also see 32 as we continue our study of string theory from a more space-time effective point of view. Then SO32 is also fixed by the requirement that a certain space-time anomaly exists. This is a repeated feature of string theory, that if you do things correctly on the world sheet, that makes close contact with doing things correctly in space-time. You can see that had you varied something else, this worldsheet problem, space-time problem, they always all go, when you do the worldsheet correctly, there's also no space-time problem. But you can see that had you done the worldsheet wrong and closed your eyes to problems, would have given rise to a space-time theory that, from a low energy point of view, would often just come to problem. Okay, we will continue our discussion on this next class, completely, and now
if you remember last time, what we did was we did all the sums over the various contractions of four-gram terms, and we got something that looked like this. What? I didn't write it down like this, but we actually did get it. All the saddle points came, and 18 alpha prime into theta 1 into A3 A4 all the two double contractions plus 324 square alpha prime. This is just 3D squared. Theta 1 2 theta 3 4. These are all the single contractions. Right, these are all single contractions, these are double contractions, and one move it right to right bar for some value of E1 equal to 2. Yeah. And then we argued that in all these terms,
This is the holomorphic part.
Yes,
similar
yes.
idea.
Yes, this is anti-holomorphic part.
Okay.
Yes. Yes. We argued that in all these terms, when you expand it out, you're going to get z or m1 and 1 minus z or m2 with m1, m2 minus 2 less than you guys, and also m1 plus m2 less than 0. This minus 2 just came from the fact that we never had anything with 1 minus z and z sitting around, and this came from some power coding that we did. Yeah. So basically, now what I'll do is I'll use a formula picked up from Boltzmann and then tell you the next step is answer. It's basically formulas for an integral e to z mod z power. I'm going to write the z power minus u plus z1, z power minus u plus z1, 1 minus z power minus t m2, 1 minus z power minus t plus into equals some product of gamma function, which we're going to write down. Unfortunately, what the gamma star is important, so fine. 2 I into 1 minus t plus into 2. I have no clue how to do the integral, but okay, this is the answer, and one thing we replace that is a minus. We replace as minus s. Okay. And we write this also as minus s. And yeah, all these, when you expand out the a1, a2, a3, of course you get really complicated k. A1, all these a1s had k1, 2, k2, 3 sort of guys sitting around inside. When you expand them out, you get really complicated structures, and I have the answer on Mathematica, but I couldn't extract anything useful out of it. So, anyway, so the final answer for gravitational amplitude is sum over m1 m2 n1 n2 m1 to m2 less than 0 n1 less than 0. What I'm going to call K N1 N2 N1 N2 into this guy.
I thought that answer should be somehow symmetric between M1 and N1 and M2 and N2.
Yes, should that be symmetric between them? I don't know, maybe if you like do some resummations, you do get it only that way. Yeah, Z to Z bar is a symmetry of this integral, so you're right. But yeah, I don't know how to do this. Okay. Anyway, so then with this answer we can do a few things. We can look at the poles and we can look at the limits and the limits. Right?
So the summation that you have goes over what values? Several.
2 to 2. All four value variable take my to true with the restriction. Yeah.
So you get a finite number of products of gamma.
Yes.
And where is the epsilons in that? Polarizations.
Oh, right. The answer K. It's K actually is a whole bunch of K12s is setting with all of them contracted with epsilons. So first thing we can do is look at the poles. The poles are so you can see that you can look at S channel poles, T channel poles, U channel poles. This guy has all three of them. Right. Let's look at the S channel poles. I didn't look at the video. Yeah. So the S channel poles.
You're looking for at one of these terms.
Yeah.
With some particular value there.
You can. I'm going to kind of do some. The first S channel pole will come from one value, one of the terms of the sum. The first T channel value will come from another of the terms of the sum. And we're going to keep them around as variables and tell you the poles come from here, the poles come from there. Okay. Right. So obviously there's one gamma of S in the numerator. Your pole is going to come from there. The S channel poles are going. So will come in -1 minus 1 minus S minus N1 minus N2 equals minus N or N is equal to 0. Right? This is the poles of the gamma function. And you can obviously say that S equals -1 plus N minus N1 plus N2. Now the smallest value this can take is N equal to 0, N1 plus N2 N1 plus N2 is at most 0, so minus N1 plus N2 is at least 0, and therefore this is greater than equal to -1. It's exactly the answer we want. This is the mass of the factor. The factor of alpha prime and 4 inside capitals. This is a nice answer. And we get 1 at every integer after -1. So yes. Similarly, you can look at T channel. T channel poles are going to come from here always because gamma doesn't have zeros, that's why I get T equals 1 minus T plus M2 minus N, and guys T equals 1 plus M2 minus N. So that's greater than equal to 1 minus 2 because M2 can go all the way down to -2 and equal to -1. Whereas similarly U channel I don't know exactly U channel is exactly the same as the T channel because N1 and N2. So yes. So you can see that all of them have the correct poles. Now we see that they seem to have the wrong residues. At least, yeah. So you can actually look at the residues. So I actually never calculated the graviton residue, but I did calculate the graviton residue. And basically it's just I never you don't know what to do. Anyway, GGG, that's right. The GGG 3-point function, it's of some T mu1 mu1 rho1 T mu2 mu2 E. It's of this form. It's basically just two identical indices tensors for it's one tensor for the monomorphic part and times an identical tensor for the anti-holomorphic part, hence dotted with the correct E's.
And those T's has a term that's linear K and a term that's cubic K, right?
And in fact, it has one more term. It has linear, it has cubic, it also has quadratic.
How does it?
Wait, it should have quadratic. Remember, right?
I thought it is eta times K and K.
There were three terms. I don't remember. But that is 1, 2, 3, 4. I have a quadratic.
So how will the indices go with quadratic?
Okay, I don't have it written in this. Let me write down what I have written. It is K1 to mu E1 Oh, sorry. The T doesn't have quadratic.
Yes.
The T into T has quadratic.
Yes.
Yeah, sorry.
The indices could have worked. Eta has two indices and K has one index.
Right. Yeah, right. So it has, I think, two linear terms and one cubic term. Yeah. So basically the point is this, that this doesn't have gamma functions, and whatever you do at the pole, suppose you look at the S equals 0 pole, you're basically going to do some calculation between these two guys, and you're going to have all these gamma functions remaining, and you don't know what to do about them, and by eyeballing the structures I can't do any calculation, so the residue seems to be wrong, because the residue you would expect it to be square of this.
Yes.
But yes, I presume there's a way to make it look correct, but I could not find it.
How many terms?
How many terms? Let me write.
So how many terms have the graviton pole?
How many terms are the graviton pole? Let's see. One of them is just one of them is what is it? N equals 1, N1 plus N2 equals 0. Right? And one of them is N equals 0, N1 plus N2 equals -1. Yes, and so that is 5 terms here, and that is 1, 2, 3, 4 terms, 9 terms.
So you have to sum them all up.
Yeah, and I could not find a useful way to sum the gammas with all the k's sitting around it. Yeah. Sorry, I couldn't do it. I reached the end of my day.
Yeah. On the other hand, the tachyon pole presumably comes from very few terms.
The tachyon pole comes from 5 terms. So yeah. Oh, right. So the calculation I did here was, look, the thing was 1 minus n equals minus n, right? So the way s could increase by 1 was either n1 plus n2 increases by 1 or n increases by 1. And so n equals 1, n1 plus n2 equals 0 has 5 terms because n1 can go from -2 to 2 and n2 can compensate. And where n equals 0 has and n1 plus n2 equals -1 has 4 terms. Yeah, I can just look at it geometrically. There's only 3 ways to compensate. So there are totally 9 terms. Where the tachyon pole have to come from n equals 0, n1 plus n2 equals 0, therefore there are only 5 terms. Okay, this is just. So yes, the residues seem to be wrong. I can't. Actually, no, we can look at the hard scattering and the Rayleigh limits now, and they are not likely.
One question in your formula, tensor times TE, were you assuming some symmetric structure for the E's, or there are symmetric actions?
Symmetric traces.
Symmetric traces. Now, the full massless pole will also come from antisymmetric traces and symmetric trace.
Oh. Right. So you have to cancel.
So it would be nice just to write what you put no assumptions on that E.
Oh, right, okay.
and then the square is really the prediction.
Okay, sure. So actually, even when you look at the tachyon pole, the graviton tachyon pole 3-point function also doesn't have the gamma functions. And also here you are going to find gamma functions, and that also I should not cancel.
Okay.
Just yeah. That's it. Right. Now look at the hard scattering limit.
So just to understand that. So suppose you're at a given value of S because you're looking at some pole.
Yeah.
So what's left is a function of, let's say, just t.
Yes.
And you're saying the gammas that appear as functions of t don't look like they cancel.
They don't. I mean, you're going to get. Yeah, see, you get one. Let's look at the plus t term, right? Right. So look, there's 1 minus t here, 1 minus t here, 1 plus t, 1 minus t. It's not obvious. I mean, they don't seem to cancel. There's probably some detailed dependence on the structures which make them cancel, which I cannot pull away. Yeah. So, our scattering limit is S go to infinity, U go to infinity, T by T equals all of them, but T by S go to sin square theta by 2. Some constant, which let's work out. It's basically the limit where it's a constant scattering angle limit for very high energies, which you can see by taking 4 guys K1, K2, K3, K4 coming in. Now you can put this to be E000 vector. You can put this to be, because we are looking at the center of mass shape. Okay, and then suppose there's some angle theta here. This would be E cos theta, E sin theta, 0. This is K4, because I do minus E because it's going in the wrong direction. And so minus E. I hope I get to what the minus in the practice. Yeah. Right. You can still, yeah.
Sorry, just one quick question about cancellation. There's this gamma function formula. Gamma of x and gamma of 1 minus x is sine. Do you know this formula? Okay, it's a nice formula and it looks like it might help given that you have a sine.
Oh.
1 over sine. There's some formula that has some identity between products of gamma functions equal to a sine. It looks like it might be relevant for you.
Okay.
Yeah, cancel.
Okay, right, thanks. Pretty good.
Yeah. Will it survive for 5 more minutes? 5 minutes will do.
Yes, 5 minutes.
Yeah, that's it. Yeah, just go into hard scattering. They will work again. Yeah, anyway. So basic point is that you can write S equals 4 E squared.
Yeah.
T equals minus 4 E squared sin square theta by 2 and Q equals minus 4 E squared cos square theta by 2. And then you just plug it in here, you throw away all subleading terms. So you take gamma as gamma of x as x bar x e power minus x. And point is, look, you have a ut as upstairs and hey. Right, so this is okay. I'll convince you that the e power minus x terms don't matter in a minute. So it's with two values of this. So the gamma of 1 minus u plus m1 you can just write as u power minus u. All the other terms are subleading. T power minus t, 1 s power s, t power minus t, s power minus s, and u power u. This is equal to s power minus 2s t power minus 2t u power minus 2u. And basically, when you look at the exponentials, you will get e power minus 2s plus 2t plus 2u, which is 0. So the st you can exponential, depending on the exponential goes away, and you just get this. And then you can. This is actually exactly the same thing we had for the 4 tachyon guy, except with factors of 2. Okay, no, not even the factors of 2. So yeah, we had actually s by 2 here. So that was 4 tachyons, but now we have s here and s. Basically, so you basically get the same limit, which is e power minus 4e squared. Shannon way of saying it. Minus sin squared theta by 2 log sin squared theta by 2 plus cos squared theta by 2 log cos squared theta by 2. Right. And so you can see it has a nice exponential solution, and it basically has the same high energy behavior as 4 tachyons. And Regge limit. Yeah, Regge limit also works out similarly to what we did in 4 tachyons. It's just a talk and stop. Sorry.
Yeah. Well, I mean, I'm sorry, you could do it in the last 5 minutes, then the first 5 minutes of the next class of your.
It's
the same. Fine.
It's exactly what happens in the not tachyons, because the math is the same. It's just all the interesting stuff is the terms you throw away.
Right. You know, the fact that high energy scattering becomes more or less universal was, at least in this regime, in the hard scattering, was explained in this paper by Gross and Mendel, in which they argued that at very high energies, you get a saddle point value of the. In fact, it becomes universal not just at tree level but also at loop level, independent of what you're saying.
Okay.
And they argue that it's dominated by the saddle point configuration of the worldsheet, whose area completely uses this. So that the high energy behavior forgets about the nature of your vertex operators except for subleading stuff. It's a genuine. Okay, thanks a lot, Ronald. It was very nice.